Learning about the basic tensor operation is an essential part of Pytorch, and it's worth to spend some time to learn it, and it's probably the first thing you should do before you do anything related to deep learning. What is going on, guys? Hope you're doing awesome, and in this video we're going to go through 4 parts. So we're going to start with how to initialize a tensor, and there are many ways of doing that. We're going to go through a lot of them, and then we're going to do some tensor math and comparison operations. We're going to go through tensor indexing, and lastly we're going to go through tensor reshaping. And I just want to say that I really encourage you to watch this video to the end so you get a grasp on these tensor operations. Even if you don't memorize them after this video, and there's probably no way you can memorize all of them, you will at least know that they exist, and that will save you a lot of time in the future. So in this video I will cover the basics, but I will also go a bit beyond that and show you a lot of useful tensor operations for different scenarios. So there's no way I'm able to cover all of the tensor operations. There are a bunch of more advanced ones that I don't even know about yet, but these are definitely enough to give you a solid foundation. So I guess we'll just get started, and the first thing I'm going to show you is how to create a tensor. So what we're going to do is we're going to do my tensor, and we're going to do torch.tensor, and we're going to do, the first thing we're going to do is a list, and we're going to do a list inside that list. We're going to do 1, 2, 3, and then let's do another list, and we're going to do 4, 5, 6. So what this means right here is that we're going to do 2 rows. So this is the first row, and then this is the second row. All right. So we're going to have 2 rows in this case, and we're going to have 3 columns. So what we could do then is we could do print my tensor, and we can run that, and we're going to just get in a nice format. So we're going to get 1, 4 for the first column, 2, 5, and 3, 6. Now what we can do as well is we can set the type of this tensor. So we can do dtype equals torch.float, and we can do, let's say, float 32. So then if we print it again, we're going to get that those are float values. Now another thing we can do is we can set the device that this tensor should be on, either CUDA or the CPU. Now if you have a CUDA enabled GPU, you should almost always have the tensor on CUDA. Otherwise, you're gonna have to use the CPU. But we can specify this using the device. So we can do device equals, and then we can set this to CUDA if you have that available. And then if we print my tensor again, we can see that the device says CUDA right here. If you do not have a CUDA enabled GPU, then you're going to have to write CPU right here. I think that CPU is also the default, so you don't have to write it, but it can help to just be specific. Now, if we run this, the device doesn't show, which means that it's on the CPU. We can also set other arguments like requires gradient, which is important for AutoGrad, which I'm not going to cover in this video, but essentially for computing the gradients, which are used when we do the backward propagation through the computational graph to update our parameters through gradient descent. But anyways, I'm not going to go in depth on that. One thing we can do as well is that you're going to see a lot when in my videos, and just if you read Pytorch code, is that people often write device equals CUDA if torch.CUDA is available, like that, else CPU. All right, and in this case what happens is that if you have CUDA enabled, the device is going to be set to CUDA, and otherwise it's going to be set to the CPU. Kind of that priority that if you have enabled, then you should use it, otherwise you're going to be stuck with the CPU, but that's all you have. So what we can do instead of writing the string here is that we can just write device like this. And now the great thing about this is that 2 people can run it, and if one has CUDA, it's going to run on the GPU. If they don't have it, it's going to run on the CPU. But the code works no matter if you have it or not. Now let's look at some attributes of tensors. So what we can do is we can as I said, print my tensor, and we just get, so we can do that again, and we just get some information about the tensor, like what device it's on and if it requires gradient. What we can also do is we can do my tensor, and we can do .dtype. So that will just, in this case, print torch.float32. And we can also do print my tensor.device. What that's going to do is going to show us what device the tensor is on. So CUDA, and then you're going to get this right here, which essentially, if you have multiple GPUs, it's going to say on which GPU it's on. In this case, I only have one GPU, so it's going to say 0, and 0 I think is the default one if you don't specify. And then what we can do as well, we can do print my tensor.shape. So yeah, this is pretty straightforward. It's just going to print the shape, which is 2 by 3. What we can do as well is we can do print my tensor.requires grad, which is going to tell us if that tensor requires gradient or not, which in this case we've set it to true. All right, so let's move on to some other common initialization methods. What we can do is if we don't have the exact values that we want to write, like in this case we had 1, 2, 3, and 4, 5, 6, we can do x equals torch.empty, and we can do size equals, let's say, 3 by 3. And what this is going to do is it's going to create a 3 by 3 tensor, and or matrix, I guess, and it's going to be empty in that it's going to be uninitialized data. But these data values that is going to be in this matrix are going to be just whatever is in the memory at that moment. So the values can really be random. So don't think that this should be zeros or anything like that. It's just going to be uninitialized data. Now, if you would want to have zeros, you could do torch.zeros, and you don't have to specify the size equals. Since it's the first argument, we can just write 3, 3 like that, and that's gonna be, so what we can do actually, we can print let's see, we can print x right here, and we can see what values it gets, and in this case it actually got zeros, but that's not what it's gonna happen in general. And yeah, if we print x after this, it's also going to be zeros. Now what we can also do is we can do x equals torch.rand, and we can do 3, 3 again, and what this is going to do is it's going to initialize a 3 by 3 matrix with values from a uniform distribution in the interval 0 and 1. Another thing we could do is we could do x equal torch.ones, and we can again do, I don't know, 3 by 3, and this is just going to be a 3 by 3 matrix with all values of 1. Another thing we can do is torch.I, and we're going to send in 5 by 5 or something like that, and this is going to create an identity matrix. So we're going to have ones on the diagonal, and the rest will be zeros. So if you're curious why it's called I, is because I, like that, is the identity matrix, how you write it in mathematics. And if you say I, it kind of sounds like I. Yeah, that makes sense. So anyways, one more thing we can do is we can do something like torch.arrange, and we can do start, we can do end, and we can do step. So, basically the arrange function is exactly like the range function in Python. So this should be nothing weird. One thing I forgot to do is just print them so we can see what they look like. So if we print that one, as I said, we're going to have ones on the diagonal and the rest will be 0. If we print x after the arrange, it's going to start at 0. It's going to have a step of 1, and the end is non-inclusive, the fifth value, or 5. So we're going to have 0, 1, 2, 3, 4. So if we print x, we're going to see exactly that, 0 and then up to inclusive 4. Another thing we can do is we can do x equals torch.linspace, and we can specify where it should start. So we can do start equals 0.1, and we could do something like end equals 1, and we could also do step equals 10. So what this is going to do is it's going to, this should be steps. So what this is going to do is it's going to start at 0.1, and then it's going to end at 1, and it's going to have 10 values in between those. So what's going to happen in this case is it's going to take the first value 0.1, then the next one is going to be 0.2, 0.3, 0.4, etc. up to 1. So just to make sure, we can print x, and we see that that's exactly what happens. And if we calculate the number of points, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So we're going to have equal to steps amount of points. So then we can do also x equals torch dot empty, as we did for the first one, and we can set the size, and I don't know, 1 and 5 or something like that. And what we can do then is we can do dot normal, and we can do mean equals 0 and the standard deviation equals 1. And essentially, so what this is going to do is it's going to create the initialized data of size 1 by 5, and then it's just going to make those values normally distributed with a mean of 0 and standard deviation of 1. So we could also do this with something like, with the uniform distribution. So we can do dot uniform, and then we can do 0 and 1, which would also be similar to what we did up here for the torch.rand. But of course here you can specify exactly what you want for the lower and the upper of the uniform distribution. Another thing we can do is torch.diag, and then we can do torch.ones of some size, let's say 3. It's going to create a diagonal matrix of ones on the diagonal, and it's going to be shape 3. So essentially this is going to create a 3 by 3 diagonal matrix. Essentially this is going to create an identity matrix which is 3 by 3. So we could have just as well used I, but this diagonal function can be used on any matrix so that we preserve those values across the diagonal. And in this case, it's just simple to use torch.ones. Now, one thing I want to show as well is how to initialize tensor to different types and how to convert them to different types. So let's say we have some tensor, and we're just going to do torch.arrange of 4. So we have 0, 1, 2, 3. And yeah, so here I set the start, the end, and the step. Similarly to Python, the step will be 1 by default, and the start will be 0 by default. So if you do arrange 4, you're just going to do, that's the end value. Now I think this is initialized as a int64 by default, but let's say we want to convert this into a Boolean operator, so true or false. What we can do is we can do tensor.bool, and that will just create false, true, true, true. So the first one is 0, that's going to be false, and the rest will be true. Now, what's great about these, as I'm showing you now, when you .bool, and I'm also going to show you a couple more, is that they work no matter if you're on CUDA or the CPU. So no matter which one you are, these are great to remember because they will always work. Now the next thing is we can do print tensor.short, and what this is going to do is it's going to create to int16, and I think both of these two are not that often used, but they're good to know about. And then we can also do tensor.long, and what this is going to do is it's going to do it to int64, and this one is very important because this one is almost always used. We're going to do print tensor.half, and this is going to make it to float 16. This one is not used that often either, but if you have newer GPUs in the 2000 series, you can actually train your networks on float 16, and that's when this is used quite often. But if you don't have such a GPU, I don't have that new of a GPU, then it's not possible to train networks using float 16. So what's more common is to use tensor.float. So this will just be float 32-bit, And this one is also super important. This one is used super often, so it's good to remember this one. And then we also have tensor.double, and this is going to be float 64. Now the next thing I'm going to show you is how to convert between tensor and, let's say you have a NumPy array. So let's say that we import NumPy as MP, and let's say that we have some NumPy array, we have NumPy zeros, and let's say we have a 5x5 matrix, and then let's say we want to convert this to a tensor. Well, this is quite easy. We can do tensor equals torch dot from NumPy, and we can just send in that NumPy array. That's how we get it to a tensor. Now, if you want to convert it back, so you have the NumPy array, we can just do, let's say, NumPy array back. We can do tensor.numpy, and this is going to bring back the NumPy array. Perhaps there might be some numerical round-off errors, but they will be exactly identical otherwise. So that was some how to initialize a tensor and some other useful things, like converting between other types, int, float, and double, and also how to convert between NumPy arrays and tensors. Now we're going to jump to Tensor Math and comparison operations. So we're going to first initialize two tensors, which we know exactly how to do at this point. We're going to do torch.tensor 1, 2, 3, and we're going to do some y to be torch.tensor, and then, I don't know, 9, 8, 7, and we're going to start real easy. So we're just going to start with addition. Now, there are multiple ways of doing addition. I'm going to show you a couple of different ones. So we could do something like z1 to be torch.empty of 3 values. Then we can do torch.add, and we can do xy, and then we can do out equals z1. Now, if we print z1, we're going to get 10, 10, and 10 because we've added these together. And as we can see, 1 plus 9 is 10, 2 plus 8, and 3 plus 7. So this is one way. Another way is to just do z equals torch.add of x and y. And we're going to get exactly the same result. Now, another way, and this is my preferred way, is just to do z equals x plus y. So real simple and real clean, and these are all identical, so they will do exactly the same operations. So in my opinion, there's really no reason not to use just the normal addition. For subtraction, there are again other ways to do it as well, but I recommend doing it like this. So we're going to do z equals x minus y. Now for division, this is a little bit more clunky in my opinion, but I think they are doing some changes for future versions of Pytorch. But we can do z equals torch dot true divide, and then we can do x and y. What's going to happen here is that it's going to do element-wise division if they are of equal shape. So in this case, it's going to do 1 divided by 9 as its first element, 2 divided by 8, 3 divided by 7. Let's say that y is just an integer, so y is, 2. Then what's going to happen is it's going to divide every element in x by 2. So it would be 1 divided by 2, 2 divided by 2, and 3 divided by 2, if y would be an integer. Now, another thing I'm going to cover is in place operations. So let's say that we have t equals torch.zeros of 3 elements. And let's say we want to add x, but we want to do it in place. And what that means is it will mutate the tensor in place, so it doesn't create a copy. So we can do that by t.add underscore x. And whenever you see any operation followed by an underscore, that's when you know that the operation is done in place. So doing these operations in place are oftentimes more computationally efficient. Another way to do in place is by doing t plus equals x. So this will also do an in place addition, similarly as add underscore. Although perhaps confusingly is if you do t equals t plus x, it's not going to be in place. That's going to create a copy first. And yeah, I'm no expert on this particular subject, so that's just what I know to be the case. To move along, let's look at exponentiation. So let's say that we want to do element-wise exponentiation. How we can do that is by doing z equals x dot pow of 2. So what that means is, since x in this case is 1, 2, and 3, and we're doing a power of 2, this is going to be element-wise a power of 2. So it's going to become 1, 4, and 9. And we can print that just to make sure. So then we get 1, 4, and 9. And another way to do this, which is my preferred way of doing it, is doing z equals x asterisk asterisk 2. So this is going to do exactly the same operation, just without the dot pow. Let's do some simple comparison. So let's say we want to know which values of x are greater than 0 and less than 0. So how we can do that is by doing z equals x greater than 0. So we can just do print z, and this is going to again also be element-wise comparison. So this is just going to be true since all of them are greater than 0. And if we do something like z equals x and then less than 0, those are all going to be false because all of the elements are greater than 0. So that's just how you do simple comparison. Let's look at matrix multiplication. So how we can do that is if we initialize two matrices, so we have x1 torch.rand, and then we do 2 and 5, and then we do x2, and then we do torch.rand and 5 and 3. How we do the matrix multiplication is we do something like x3 equals torch.mm, x1, and x2. And then the out shape of this will just be 2 by 3. An equivalent way of doing the matrix multiplication is you can do x3 equals x1.mm and then x2. So these are really equivalent. Either you write out the torch.mm or you just do the tensor, and then it has this operation as an attribute to that tensor. Now let's say that we want to do some matrix exponentiation, meaning so we don't want to do element-wise exponentiation, but rather we want to take the matrix and raise the entire matrix. So how we can do that? Let's do matrix exponent, and let's just initialize it to torch.rand of 5 and 5. And then we can do something like matrix.exp or underscore exp, and then matrix underscore power, and then we can send in the amount of times to raise that matrix. So we can do something like 3, and this would be equivalent, of course, to doing matrix exponent and then matrix multiply by itself, and then matrix multiply again by itself. If we're curious how that looks like, we can just print it, and it's going to be the same shape. So it's going to be a 5 by 5, and yeah, these values don't really mean anything because their values are random. But at least we can see that it sort of seems to make sense. If we do the matrix multiplication 3 times, we will probably get something that looks like that. Now let's look at how to do element-wise multiplication. So we have x and we have y. So we have 1, 2, 3, 9, 8, 7. What we can do is we can do z equals x and then just star y. So that will just be an element-wise multiplication. And so if we print z, that should be, 1 times 9, and then 2 times 8, so, and then 3 times 7. So it should be 9, 16, and 21. So if we print that, we see that we get exactly 9, 16, and 21 as we expect. Another thing we can do is the dot product. So essentially that means taking the element-wise multiplication, then taking the sum of that. But we can do that instantly by doing torch.dot and then x and y. So that would just be the sum of 21, 16, and 9. So we can just do print z for that, and we can see that the sum is 46. Something a little bit more advanced is a batch matrix multiplication. And I'm just going to initialize. So I'm just going to initialize the matrices first, or tensors, I guess. So we're going to do batch equals 32, n equals 10, m equals 20, p equals 30. So this doesn't make any sense yet, but we're going to do tensor 1, and we're going to do torch.rand, and then we're going to do batch, and then n, and then m. So we have 3 dimensions for this tensor. Essentially, that's what means when we have batch matrix multiplication. If we just have 2 dimensions of the tensor, then we can just do normal matrix multiplication, right? But if we have this additional dimension for the batch, then we're going to have to use batch matrix multiplication. So let's define the second tensor. So that's going to be torch.rand, and it's going to be batch, and then it's going to be m, and then it's going to be p. If we have the tensors structured in this shape, then we're going to do out after batch matrix multiplication. It's just going to be torch.bmm of tensor 1 and tensor 2. And so what happens here is that we can see that the dimensions that match, that are equal, are these ones right here. So it's going to do matrix multiplication across that dimension. So the resulting shape in this case is going to be batch, n, and p. So we're going to get batch, and then n, and then p. Next, I want to cover something else, which is some examples of a concept called broadcasting that you're going to encounter a lot of times in both NumPy and Pytorch. So let's say we have 2 tensors. We have x1, which is just a random, uniformly random 5x5 matrix. And then we have x2, which is torch.rand, and let's say it's 1x5. Now let's say that we do z equals x1 minus x2. And mathematically, that wouldn't make sense, right? We can't subtract a matrix by a vector. But this makes sense in Pytorch and NumPy. And why this makes sense, or how does it make sense? It makes sense in that what's going to happen is that this row is going to be expanded so that it matches the row of the first one. In this case, so this one is going to be expanded, so we have 5 rows where each column are identical to each other, and then the subtraction works. So in other words, this vector here is going to be subtracted by each row of this matrix. That's what we refer to as broadcasting, when it automatically expands for one dimension to match the other one so that it can actually do the operation that we're asking it to do. We can also do something like x1 and then element-wise exponentiation to x2. So again, mathematically, this doesn't make too much sense. We can't raise this matrix element-wise by something that doesn't match in the shape, but it's going to be the same thing here in that it's going to copy across all of those rows that we wanted to element-wise raise it to. So in this case, it's going to be again be a 5x5, and then it can element-wise raise from those elements. Now let's look at some other useful tensor operations. We can do something like sum of x, which is going to be torch.sum, and then we can do x, and we can also specify the dimension that it should do the summation. In this case, x is just a single vector, so we can just do dimension equals 0. Although if you have a, like we did here in tensor 1, where we have 3 dimensions of the tensor, you can specify which dimension it should sum over. Another thing we can do is we can do torch.max. So torch.max is going to return the values and the indices of the maximum values. So we're going to do torch.max of x, and then we also specify the dimension for which we want to take the maximum. Again, in this case, we just have a vector, so the only thing that makes sense here is dimension 0. You can also do the same thing, values, indices, but you can do the opposite. So the torch.min instead of torch.max. Then we can again do x, dimension equals 0. We can compute the absolute value by doing torch.absolute value or torch.abs of x, and that's going to take the absolute value element-wise for each in x. We could also do something like torch.argmax of x, and then we specify the dimension. So this would do the same thing as torch.max, except it only returns the index of the one that is the maximum. I guess this would be a special case of the max function. We could also do the opposite. So we could do torch.argmin of x and then across some dimension. We could also compute, and I know these are a lot of operations, but so we can also do the mean. So we can do torch.mean, but to compute the mean, Pytorch requires it to be a float. So what we have to do then is x.float. And then we specify the dimension. In this case, again, we only have dimension 0. If we would, for example, want to element-wise compare two vectors or matrices, we can use torch.eq, and we can send in x and y. And this is going to check essentially which elements are equal, and that's going to be true. Otherwise, it's going to be false. In this case, if we scroll up, we have x and y are not equal in any element. So they are all going to be false. Essentially, if we print z, this is just going to be false, 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 because none of them are equal. Other thing we can do is we could do torch.sort, and here we can send in y, for example. We can specify the dimension to be sorted, dimension 0, and then we can specify descending equals false. So essentially, we're gonna, in this case, sort the only dimension that y has, and we're gonna sort it in ascending order. So this is default, meaning it's going to sort in ascending order. So the first value, the first element is going to be the smallest one, and then it's just going to be in increasing order. And what this returns is two things. So it also returns the sorted y, but then it's also going to return the indices that we need to swap so that it becomes sorted. All right, these are all a lot of tensor operations, but so there are not that many left on this one. So one more thing we can do is we can do torch.clamp, and we can send in x, for example, and then we can do min equals 0. So what this is going to do is it's going to check all elements of x that are less than 0. It's going to set to 0. In this case, there are no max value, but we could also send in max equals, 10, meaning if any value is greater than 10, it's going to set it to 10. So it's going to clamp it to 10. But if we don't send any value for the maximum in, then we don't have a max value that it clamps to. So if you recognize here, if this is going to clamp every value less than 0 to 0, and any other value greater than 0, it's not going to touch, then that's exactly the rel function. So torch.clamp is a general case, and the rel is a special case of clamp. So let's say that we initialize some tensor, and we have, 1, 0, 1, 1, 1, and we do this to dtype torch.bool, so we have true or false values. Then let's say that we want to check if any of these values are true. So we can do torch.any of x, and so this is of course going to be true because we have most of them to be true, which means that at least one is true. So this will be true. But if we instead have z equals torch.all of x, this means that all of the values needs to be 1, meaning there cannot be any value that's false. So in this case, this is going to be false since we have one value right here that's 0. I also want to add that right here, when we do torch.max, you could also just instantly do x.max and then dimension equals 0. And you could do that for a lot of these different operations. You could do that for absolute value, for the minimum, for the sum, argmax, sort, etc. So here I'm being very explicit in writing torch everywhere, which you don't need to do unless you really want to. So that was all for math and comparison operations. As I said in the beginning, these are a lot of different operations, so there's no way you're going to memorize all of them, but at least you can sort of understand what they do, and then you know that they exist. So if you encounter a problem, then you can think of, I want to do this, and then you know what to search for essentially. So let's now move on to indexing in a tensor. So what we're going to do for tensor indexing, we're going to do, let's say we have a batch size of 10 and we have 25 features of every example in our batch. So we can initialize our input x, and we can do torch.rand, and we can do batch size, comma features. And then let's say we want to get the first example. So we want to get the features of the first example. Well, how we can do that is we can do x of 0, and that would get us all of the 25 features. So I'm just going to write .shape, and this is equivalent to doing x0 comma all, like this. So what this would mean is that we want the first one, the first example in our batch, and then we want all the rest in that specific dimension. So we want all the features, but we could also just do x of 0 directly. Now let's say that we want the opposite. So we want to get the first feature for all of our examples. Well, how we can do that is we can do x of all and then 0, which means that we will get the first feature, right? The first feature over all of the examples. So if we do .shape on that, we're just going to get 10 right there, since we have 10 examples. Now let's say that we want to do something a little bit more tricky. So we want to get the third example in the batch, and we want to get the first 10 features. How we can do that is we can do x of 2. So that's the third example in the batch. And then we can do 0 and then to 10. So what this is going to do essentially, it's going to create a list of, so 0 to 10 is essentially going to create a list. So 0, 1 up to 9. And so what this means is that Pytorch is going to know that we want the second, or I guess the third row, and then we want all of the elements of 0 up to 10. We could also use this to assign our tensor. So we could do x of 0, 0, and we can just like set this to 100 or something like that. And of course, this also works for this example right here and the previous ones. Now let's say that we want to do something more fancy. So we're going to call this fancy indexing. And we can do something like x is torch.arrange of 10. And then we could do indices, which is going to be a list of, let's say, 2, 5, and 8. What we can do then is we can do print x of indices. So what this is going to do is it's only going to pick out, I guess in this case, the third example in our batch, the 6th example in our batch, and the 9th example in our batch. Since here we just did torch.arrange 10, this is going to pick out exactly the same values. So it's going to pick out 3 elements from this list right here, and it's going to pick out the value 0, 5, and 8 exactly matching the indices. So if we would do, if we would print that, we would see that we get exactly 2, 5, and 8. What we can also do is, let's say we do torch.rand, and we do 3 and 5. And then let's say that we want some specific rows. So we do rows equals torch.tensor of 1 and 0. And we specify the columns as well. So we do torch.tensor of, 4 and 0. Then we can do print x of rows comma columns. What this is going to do is it's going to first pick out the first, or I guess the second row and the 5th column, and then it's going to pick out the first row and the second column. Yeah, that's what it's going to do. It's going to pick out 2 elements. So we can just do that real quick. So we print the shape, and we see that it's going to pick out 2 elements. Now let's look at some more advanced indexing. So let's say again we have x is torch a range of 10, and let's say that we want to just pick out the elements that are strictly smaller than 2 and greater than 8. So how we can do that is we can do print x, and then we can do list, and then we're just going to do x less than 2, and then we can do or x is greater than 8. So what this means is it's going to pick out all the elements that are less than 2, or it's going to pick out, so it's going to pick out the elements that are less than 2, or if they're greater than 8. Essentially, in this case, it's going to pick out the 0 and the 1, and it's going to pick out the 9. So if we just print that real quick, we'll see that it picks out 0, 1, and 9. And what you could also do is you could replace this with an AND sign. So this would be, it needs to satisfy that it's both smaller than 2 and greater than 8, which of course wouldn't be possible. So if we run that, that would just be an empty tensor right there. I want to show you another example of this. We could do something like print x, and then inside the list, we could do x dot remainder of 2, and we can do equal 0. So this is going to do just if the remainder of x, x modulus 2 is 0, then those are the elements we're going to pick out. Essentially, these are all the even elements, right? So we're going to pick out the even elements, which are 0, 2, 4, 6, and 8. So if we print that real quick, we again see that we have 0, 2, 4, 6, and 8. So you can imagine that you can do some pretty complicated indexing using stuff like that. So this is quite useful stuff. Also, some other useful operations are torch.where. So we can do print torch.where, and we can do something like a condition. We're going to set x is greater than 5. And if x is greater than 5, then all we're going to do is we're just going to set the value to x. And if it's not greater than 5, then we're going to return x times 2. So what this is going to do is if the value is 1, for example, then this condition is not satisfied. And then we're going to go and change it to x times 2. So if we print this, we're going to get this right here. So 0 just stays 0 because 0 times 2 is still 0. 1 times 2 is going to be 2. 2 times 2 is 4. 3 times 2 is 6. 4 times 2 is 8. And then 5 times 2 is 10 because it's not strictly greater than 5. And then moving on, it satisfied the condition. And then we just returned the x value, which was 6, 7, 8, and 9 for the last values. Another useful operation is, let's say we have a tensor and we have 0, 0, 1, 2, 2, 3, 4. What we can do to just get the unique values of that tensor, so that would be 0, 1, 2, 3, 4, we could do pretty explanatory. We could do dot unique. And if we print that, we're going to get exactly what we expect. We're going to get 0, 1, 2, 3, 4. Another thing we can do is we could do x dot n dimension. What this is going to do is it's going to check how many dimensions of x that we have. So what that means is, in this case, we have a single vector, which is going to be a single dimension. But so if we just run that, first of all, we're just going to get 1 because it's just a single dimension. But let's say that we would have a 3-dimensional tensor. We would have something like 5 by 5 by 5. And this would then, if we run something like that has this shape, then n dimension will be 3 in that case. Another thing you could also do is you could do print x.numal, and that will just count the number of elements in x. So this is quite easy in this scenario since we just have a vector. But if this was something larger with more dimensions and more complicated numbers, then this can come useful. So that's some pretty in-depth on how to do some indexing in the tensor. Let's move on to the final thing, which is how do we reshape a tensor. Again, let's pick our favorite example. We have a torch.range of 9. So we have 9 elements. And let's say we want to make this a 3x3 matrix. So we could do x, and let's do 3x3. We could do x.view, and then 3x3. So if we print x and then 3x3.shape, we're going to get the shape is 3x3. So that's one way. Another way we can do that is by doing x 3x3 is going to be x.reshape and then 3x3. And this is also going to work. So view and reshape are really very similar, and the differences can be a bit complicated, but in simple terms, view acts on something called contiguous tensors, meaning that the tensor is stored contiguously in memory. So if we have something like, if we have a matrix, really that's a contiguous block of memory with pointers to every element to form this matrix. So for view, this memory block needs to be in contiguous memory. For reshape, it doesn't really matter. If it's not, then it's just going to make a copy. So I guess in very simple terms, reshape is the safe bet. It's always going to work, but you can have some performance loss. And if you know how to use view, that's going to be superior in many situations. So I'm going to show you an example of that. So this is going to be a bit more advanced. So if you don't follow this completely, that's fine. But if we, for example, do y equals x 3x3, and then we do dot t. So what that is going to do, it's going to transpose the 3x3. Just quickly, this, and when we do view on this one, and we sort of print it, so we can do print x 3x3, we get 0, 1, 2, 3, 4, 5, 6, 7, 8. If we do print of y, which is the transpose of that, we're going to get 0, 3, 6, 1, 4, 7, 2, 5, 8. Essentially, if that would be a long vector, right? That would be 0, 3, 6, 1, 4, 7, 2, 5, 8. Originally, it was constructed as a 0, 1, 2, 3 up to 8. And so if we see right here, for one element jump in y, there's a 3 element jump in the original x that we constructed or initialized. So comparing to the original, we're jumping steps in this memory. At least this is how I think about it. And again, I'm no expert on this, but my idea is that we're jumping in this original memory block. We're jumping different amounts of steps. So this now transposed version is not a contiguous block of memory. So then if we do something like y.view, and then we do 9 to get back those 9 elements, we're going to get an error which says that at least one dimension spans across 2 contiguous subspaces. Use .reshape instead. So what you can do is you can use reshape, and that's a safe bet, but you could also do y.contiguous and then .view, and that would work. So again, this is a bit complicated, and even I need to explore this in more detail, but at least you know this is a problem to be cautious of, and a solution is to do this contiguous before you do the view. And again, the safe bet is to just use .reshape. So moving on to another operation, let's say that we have x1 and we have it initialized to some random 2x5 matrix, and we have x2 to be some torch.rand, and let's say it's also 2x5. Then what we can do is if we want to sort of add these two tensors together, we could use torch.cat for concatenate, and we can concatenate x1 and x2. And it's important right here that we send them in together in a tuple. And then we specify the dimension that we want them to be concatenated along. So dimension 0, for example, would add them across this dimension. If we just do dot shape of that, we're going to get 4 by 5, right? Which makes sense. If we instead do something like print torch.cat of x1, x2, and then we choose dimension 1, then we're going to add across the second dimension, so we're going to get 2 by 10. Now let's say that we have this x1 tensor right here, and what we want to do is we want to unroll it so that we have 10 elements instead of this 2 by 5 elements. So how we can do that is we can do something like z equals x1 dot view, and then we can do -1. So this is Pytorch is gonna magically know that you want to just flatten the entire thing by sending in this -1. So if we do print z.shape, then we're gonna get 10 elements, and that's exactly what we wanted. So, but let's make this a little bit more complicated. Let's say that we also have a batch of 64, and let's say we have x to be torch rand of batch and then 2 and 5. So what we want to do is we want to keep this dimension exactly the same, but we're okay to concatenate or put together the rest of them, and we can even have another one right here. It's still going to work, but let's just say we have 3 in this case. So how we can do that is we can do z equals x.view of batch and then -1. So this is going to just keep this dimension, and it's going to do -1 on the rest. If we would do print z.shape on that, that would be 64 by 10. Now let's say that you instead wanted to do something like switch the axis. So you would still want to keep the batch, but you would want to switch these two or something like that. So you want this one to show 5, and you want this one to show 2. Now how we do that is you could do z is x.permute, and then you're going to specify the dimension that you want them to be at. So we want to keep dimension 0 at 0. For the second one, we want the second dimension, right, in the original to be on the first dimension. So we're going to put 2 right here. Then we want the dimension 1 to be on dimension 2. So we're going to do 0, 2, and 1. So let's say that you wanted to transpose a matrix. That would just be a special case of the permute function. So I think we used .t up here, and so this is very convenient since we have a matrix right here. But if you have more dimensions, you would use .permute, and you can also do .permute on a matrix. And so the transpose is really just a special case of permute. But so if we print z.shape now, we're going to get 64, 5, and 2. I'm going to do another example. Let's say we have x and we have torch.arrange of 10. So this would be, 10 in size. Let's say that we want to add 1 to it. So we want to make it a 1 by 10 vector. How we do that is we would do x and then unsqueeze. And then let's say we want to add the one to the front, or the first one, we would do unsqueeze 0. And so if we print that shape, we're going to get 1 by 10. Now, if you instead want to add it across the other one, you would do, so you want to have it as a 10 by 1, you would do x.unsqueeze of 1. And then if we just print that shape, then we're going to get 10 by 1. Let's say we have something like x is torch.arrange of 10, and then let's do unsqueeze 0, and then unsqueeze 1. So this shape is 1 by 1 by 10. And then let's say that we want to, remove one of these so that we just have 1 by 10. Perhaps this is a bit unsurprising. We can just do z equals x.squeeze of either 0 or 1. So we can just do x.squeeze of 1. And if we now print z.shape, we're going to get a 1 by 10 right there. I think this was a quite long video, but hopefully you were able to follow all of these tensor operations, and hopefully you found it useful. I know that there's a lot to take in, a lot of information, but if you really, get the foundation correct, then everything is going to become a lot easier for you when you actually start to do some more deep learning related tasks. So this is stuff that's boring that you kind of just need to learn. And when you got that, everything else becomes easier. So with that said, thank you so much for watching the video. If you have any questions, then leave them in the comment below. And yeah, hope to see you in the next video.